And welcome to your next lesson on further mathematics, GCSE. So we're going to be looking at calculus for the last time now, looking at some applications of differentiation. So we've seen what differentiation is, how to perform it, um, and now we're going to see how it's applied in other mathematical contexts as well as in a real world context, real world scenarios. So we're going to first look at tangent and normal lines. Maybe you've heard of these before, normally more relating to a circle, but we can find these lines when dealing with any curve, and they're very useful lines to be able to know. We're going to look at velocity and acceleration, so real world quantities, how these two are related to position via differentiation, which is then really useful because if we know one quantity as, say, a function, we can then differentiate to find others. And finally, we can look at optimization problems, which is a super useful technique, to find the optimal solution in a particular scenario, which, would obviously be very valuable. So yeah, we'll see how that works as well. So first of all, tangents and normals. So um, let's take a set of axes like this, and say if we take a particular function like this, and if I was to plot this, well, you can see this is essentially just a quadratic, isn't it? And say we've got a particular point here at when x equals 2, and we want to find the tangent to this line at that point. So what is the tangent line to this curve? It's going to look something like this. So it's basically a straight line that will just touch that curve at that one particular point. So it doesn't intersect it. It doesn't like cut through it. It just essentially touches it at that one point. So you could imagine almost if you had like a straight plank or something and you put it on this curve, like it's that one point it's going to touch. And we want to find that. So how do we find that? So there's the key property with a tangent line is at that point at which it touches, it's going to have the exact same slope as that function, which perhaps you can see there if you just look at the slope of that straight line. That curve, even though the gradient is constantly changing, at that particular point, is it exactly the same slope? And it has to be. By definition, a tangent line will have the same slope at that one point, and so that's what we use. So um, what we do, say if we just simplify this function first of all, because it's kind of as a big fraction, let's get it into this kind of form. Because okay, if we're trying to find the slope at this particular point, we know we need to use differentiation. So we want to be able to differentiate this. So yeah, when we get it into this form, this like little sequence of monomials, we can then differentiate that by using our power rule that we have. So you see the 4 just disappears entirely. The minus 5 over 6x will just, well, be minus 5 over 6. And then the 1 over 6, well, we times that by the power of 2 on the x squared term. And that becomes, minus 1 over 3 instead. And we're not 1 off the power. So there we go. So we can use our understanding of how to differentiate polynomials there. And okay, right. So this is now like our gradient function, which will produce the gradient at any point along that curve, but we want the gradient specifically at that point, x equals 2. So we substitute in 2. We just, have to evaluate out what that expression comes to. So it's minus 5 over 6 minus 2/3. Got to use a bit of knowledge of fractions there to then find out that the gradient is going to be minus 3 over 2. So that's the useful piece of information that we want there. The gradient at that specific point is going to be minus 3 over 2. And okay, now we use our understanding of tangents that we know, okay, the tangent line is going to also have that same gradient. So, right, so straight line, we know it has the form y equals mx plus c, doesn't it? Where m is the gradient, c is the y-intercept, but we can't read the y-intercept here. Once we've got the gradient, we then need to know a point on that line in order to then find out what the c is going to be. So, so this is just coming from regular GCSE math syllabus, which I assume you're already quite familiar with. Finding the equation of a straight line. So we need a point on that straight line. Well, the only point we could find is the point when it touches the curve, because we know what the curve is, and so we could find that point where x equals 2. So say if we substitute 2 into our original function, not f dash, but the actual function f, and you'll see we'll get this, because minus 5x would then be minus 10, minus 2 squared would then be minus 4. Note, because the minus sign is not included in that squaring, is it? So it's going to be minus 4, not plus 4. And if we evaluate that out, you get 5 over 3. And so, okay, so we know the coordinate at that point is 2, 5 over 3. And we know the gradient at that point is minus 3 over 2. So now, using our understanding of straight lines, we've got everything we need to find out what the gradient of, what the equation of that line is going to be. So, like I said, it's going to be y equals mx plus c. This is our general form for any straight line. We can put in our gradient, and now we can substitute in our coordinate. Y equals 5 over 3, x equals x equals 2, sorry. And so minus 3 over 2 times by 2 is there's just going to be minus 3. So we get this little simple expression for c, which we can just rearrange, and we find c equals 14 over 3. So now we've got everything we need. We piece it all together. You see the equation at line is going to be y equals 14 over 3 minus 3 over 2x. I've just kind of swapped the terms around there so that we don't have a leading minus sign, but you could easily put it the other way around. It's fine. So yeah, so that's kind of the process for finding a tangent line. That we need to use the fact that both that line and the curve have, at that point, are going to have the same coordinates, but they're also going to have the same gradient as well. And so we can use our function f of x to then determine what the that coordinate is and what the gradient is at that point, and that allows us to then find what that straight line is. And the process for finding the normal line as well, we'll see in a minute, is very similar. But one thing I want to touch on first, you could have a slightly different type of problem, which could look something like this. Yeah, where, going back to what we saw before about piecewise functions, you could have something like this, where maybe you're told we have this function f of x, like this graph follows this function f of x up to point 2, and then it goes at a straight line from that point onwards at the same slope. We could have used everything we just did a moment ago to find out then what that straight line would be, and it would still just be 14 over 3 minus 3 over 2x. And if we then piece that together to create this function g of x, we could then define that piecewise like this. So if you had a situation like this where it's like you've got a curve up to a certain point and then it just continues going in the same straight line, that's kind of like the same thing. You're basically finding the tangent at that point, and then you follow that tangent from that point onwards. So slightly different scenario there, but the process of working out would be exactly the same. This is less likely for you to come across, but you could. So I thought I'd just mention it so that it wouldn't throw you off. But going back to what we just had a moment ago, our curve and our tangent line. Let's say if I draw in another line like this now, and this is going to be a normal line, and it's a normal line at the point x equals minus 8. So so you see this will intersect the curve, and it intersects precisely at 90 degrees. That's what we want, is that normal line, which is another very useful line to know and how to find out. So we're told they intersect at minus 8, and that's on the x-axis as well. So we know that we already know that full coordinate. It's going to be minus 8, 0, isn't it? How do we find this normal line? Well, it's going to be a very simple, a very similar process. So first of all, we want to find out what is the gradient of our curve at that point, minus 8. So, okay, let's recall our f dash of x that we found earlier. And substitute in our x equals minus 8, and we can generate what the gradient is going to be at that particular point, which will be 11 over 6. And okay, now we want to find the equation of this straight line, which is going to be of the same form of y equals mx plus c. And we can substitute in our gradient, and we can substitute in our coordinate again to find out what the c is. But the key thing to note here is the gradient is not going to be 11 over 6, is it? it's going to be minus 6 over 11. So again, this is coming from the regular GCSE syllabus here. Perpendicular gradients will multiply to produce minus 1. Or you can see one gradient is going to essentially be minus the reciprocal of the other. So if the gradient of this curve is 11 over 6, then the perpendicular gradient, the one that cuts at 90 degrees, is going to be minus the reciprocal of that. So we do minus 6 over 11 instead. So make sure you're very familiar with that property of perpendicular gradients. And you can see from here, it's basically the same process. So, okay, let's substitute in our coordinate. Minus x, x is minus 8, sorry. And y is 0. This gives us a little expression. We can solve for c. And we get minus 48 over 11. And we can then put that back into our original equation. You see there, I've factored out the factor of minus 6 over 11. But you don't have to do that. And there we go. We get another equation for that perpendicular line now. And you could have then maybe another question that then asks you to find where do these two straight lines intersect themselves. And that would then be a simultaneous equations problem, wouldn't it? And you could solve for that as well if you wanted. So that's kind of a way in which this question could progress further. But we won't be doing that right now. But yeah, so that's tangents and perpendicular lines and how we find those. So the key to note is, for a tangent line, where it touches the curve, it's going to have the same coordinates and the same gradient. For the perpendicular line, very, very similar. It's going to have the same coordinates, but the perpendicular gradient, so minus the reciprocal of the gradient of the curve at that point. So there's that one little extra step, but apart from that, it's the same, isn't it? So let's move on. Velocity and acceleration. So like real world, metrics here. And we want to see kind of how they're related via differentiation. So let's take a little graph like this, and I've got P against T, where P is the position of some object along a line, and then T is time. And say if we have this equation, quite a typical equation you might come across, showing the position of something moving along a line. And if we plot that, it will look something like this. And this could be the example of anything. Like we're going to take, like, say, the example of like a ball that is being kicked straight up in the air. So you see if it gets kicked straight up, what's going to happen? It's going to go up and it'll gradually slow down and then it'll come all the way back down again. And that's kind of what this graph is modeling, except for the fact that it's not just moving through space, it's moving through time as well, this x-axis. So when we draw it like this, it's kind of looking more like this. But what this is modeling is a scenario where a ball is just going straight up and straight back down. So you see the position goes up and it goes down as we go through time. So that's kind of like the way to look at this graph. Very common scenario you might come across. And this is going to be measured in meters. So what about if we wanted the velocity of this? So we don't just want the position of where the ball is at any moment in time. We want to know what is its speed going to be? Well, if we know what the position is in terms of time, p in terms of t, we can then find the velocity, which would be this. And you might notice here, what I've done, I've basically just differentiated, which I hope would make intuitive sense. You think about what speed is. Speed is basically how quickly is your positioning, how quickly is your position changing. So if your speed is really, really high, it's like you're then moving quickly, like your position where you are from one moment to the next is changing more quickly. Whereas if your speed is slow, it's then not changing so quickly. So it kind of makes sense why it would be that. And it's the reason why we then express speed or velocity in terms of meters per second. So you think about if we was differentiating a distance or a position in this case, which is measured in meters, Well, if you differentiate, you think about when you're finding a gradient, you're doing like a difference in distance divided by a difference in time. Well, that's why you end up then getting this unit of meters over seconds. So that's all kind of coming together, and you can sort of see why this would be the case. And we can then even go one step further to find acceleration, which is then the rate of change of your speed, isn't it? So if you're accelerating, it means you're speeding up, you're going faster. And so we can then differentiate velocity to find acceleration. So if we differentiate that little expression for velocity, you see that's just a linear expression. The acceleration is just -2, so there's no t in at all anymore. It's basically just a constant rate. Um, and what you might have seen this before. You don't tend to encounter acceleration quite as much, but if you have, you've probably seen the units are like meters per second squared. And where that comes from is because, well, this is a rate of change of velocity, isn't it? And velocity is meters per second. So we're doing meters per second per second. And so it's like meters divided by second again. It gets, divided by second squared. So that's kind of where that comes from, because it's a rate of change of velocity. It's meters per second over seconds again. Um, so there we go. So we can see how they're related. So if we know what position is, we can then differentiate to find velocity. We could differentiate again to find acceleration. So acceleration would then be the double derivative of position. So we've taken a little look at double derivatives, haven't we? And so now, using this knowledge, we could then find out all sorts of things. So you could take, say, a question of what is the maximum height the ball reaches, um, which would be this point up here, isn't it? The maximum height. Well, we can then take these kind of real world questions and translate them essentially into mathematical problems. Because notice what we're doing there, we're basically just finding a turning point. So what we're doing is we're taking our function for position, we differentiate it, we set it equal to 0, and that will tell us where that maximum point is. So you can see that's basically asking when is the velocity 0, because the derivative of position is velocity. If we're setting the derivative to 0, you're basically setting velocity to 0. Which again, I hope that kind of makes intuitive sense, because you imagine a ball going up, like it gets kicked up and it's slowing down, slowing down, slowing down, and then right at that maximum point, it's temporarily stationary, and then it starts to fall back down and it starts speeding up again. But at that moment in the middle is where the velocity is just for a second is stationary. So that kind of makes intuitive sense, I hope, why we set that to 0. We could ask another question like, how long did it take for the ball to reach the ground again? So you see it starts at the ground, we kick it straight up, and then eventually it comes back down again. That's going to be essentially this point over here. So you see what we're doing here. We're basically trying to find the roots of this quadratic. You see where it intersects that x-axis. Like we can see that one of them's at 0, but we're basically trying to find what the other one is. So again, we're taking like a real world problem, like how long does this ball take to reach the ground again? And we can translate that into a math problem, which is find the roots of this quadratic. Which, okay, 10t minus t squared, set that equal to 0. That's where the roots occur. And you could just solve that quadratic and you'll find out what that time is. We could go one step further and find out, okay, what speed was the ball going when it hits the ground? So, okay, maybe we've found out what time it hits the ground, and we now want to know how fast was it going when it hit the ground. That might be something you wanted to do if you want to determine how violent was the impact or something of something. So, okay, what we could do is we could then take that time that we worked out, substitute it into our function for v of t. Basically the derivative of position. So 10 minus 2 times whatever the time is you've got there. And that will give you then what speed it was going. And if you do that, I hope you give that a go yourself. You should find that velocity is going to be negative. And don't let that throw you off. Like that's not actually incorrect. The reason why it's negative is because it's going downwards. So here, velocity going up is positive and velocity going down is negative. Same thing with acceleration. So that's an important thing to note here. When you've kind of got a direction to things, um, it can be either positive or negative. So that's all to say on that. So that's a really important relationship to know between position, velocity, and acceleration. A lot of real world scenarios you're going to encounter will involve position, velocity, and maybe acceleration. Normally more position and velocity, and you need to know that relationship of how velocity is the derivative of position, and perhaps then again to get acceleration, and how to translate these real world problems into then these mathematical problems, which you then know how to solve. That's why we learn all these mathematical techniques. So one last type of problem, very useful type of problem known as optimization problems. So this is a situation when you're um, essentially kind of got like a bit of a trade-off going on between various things, and we want to find what is the optimal solution. So that there's, you go too far one way, and that the solution you get is not too great. You go too far the other way, it's not that great. There's some kind of sweet spot in the middle where it's the best possible solution, and we're trying to find what that point is. Um, if you're thinking that kind of sounds a bit like a turning point situation, you'd be right, and so that's you can kind of see like how differentiation is going to come in there. But let's look at this through an example. So say if here we've got like a juice carton here that a company might be designing, and they have these kind of dimensions. They've got a width of it of X. They want then the length of it to be twice the width, so it has to be 2x. And the height, it can be some other amount, we label that H. And this is the situation we have here. A company wants to design a juice carton that minimizes the material required to make it, because why wouldn't you? Because then it would save you money, wouldn't it? Um, but we know the carton has to have 300 centimeters cubed of volume, that because we want it to hold that much juice. We want to find, okay, what values of X and H will give us the minimum surface area required to produce this carton based on these constraints. So whenever you get a question that's asking you to find the minimum of something or the maximum of something, this is like an optimization problem. So that for various values of X and H, you're going to get different values for the surface area and therefore the cost to make this carton, and we want to find where is that sweet spot in the middle where it's at its minimum, so it's going to be the cheapest to produce this carton. And straight away this should be making you think, I'm gonna have to use differentiation here, because we know we've seen this before, how we use differentiation to find minimum points and maximum points of a function. So first of all, we need to think, what function are we using here? Well, what we're interested in is surface area. So we need to use a bit of our understanding of geometry here to calculate the surface area. So I've given us a relatively nice one here because it's just a cuboid shape. So first of all, if you think of the base of this carton is going to be 2x times x, which is then going to be the same as the top. So we've got 2x squared times 2 essentially would be 4x squared. And then finally, if you not finally, secondly, if you look at the right and the left hand side, they're going to both be equal to x times h, aren't they? So you've got x times h times 2, so 2xh. And then finally, we've got essentially the front and the back of the carton, which you can see is going to be 2x times h. So you get 2xh, but then you times that by 2 because you've got the front and the back. So it's going to be 4xh. And so, okay, symbolically, in terms of x and h, we can see this is going to be the surface area, isn't it? Which, I can collect like terms there to simplify a little bit. We get 4x squared plus 6xh. So, if we wanted to then optimize this. Like we're trying to find the minimum point of this. Right, so we've seen how to do this. What we need to do is we need to differentiate this and then set that derivative equal to 0, and that will find where that turning point is, that minimum point. Um, and typically in these kinds of scenarios, you only get something where there's just one turning point, and that will then be the one you need really. Um, but you might see the problem here is that there's two unknown variables here. There's the x and there's the h, and we can't differentiate with respect to both. Um, I mean, there's kind of a way you can differentiate here, but it's kind of beyond the scope of GCSE. Because you see, both of those variables are going to affect the surface area, aren't they? If you change the value of x, it's going to change the surface area. If you change the value of h, it would change the surface area. So what we need to do here, we need to eliminate one of the variables. Now, when I use that word eliminate, if you're thinking, oh, that sounds like simultaneous equations, we have the elimination method, don't we? That's exactly what we need to do here. So what we need is another equation, another constraint on this system. So we think, okay, what other information have we got in this question? Well, we've been told the volume has to equal 300 centimeters cubed. Okay, well, let's look at the volume of this carton. So we know volume of a cuboid is relatively straightforward. It's going to be the 2x times the x times the h, length times width times depth. And you'll see that will be 2x squared times h. And we know that has to equal 300. So what we can do here, you see, if we rearrange that, we've now got a little expression for h in terms of x. And what I'm going to do is I'm going to take that and I'll substitute that back into my little expression for surface area. So 4x squared plus 6xh becomes now this. So 6xh, if I replace the h with 300 over 2x squared and simplify this a little bit, you can check that for yourself. You'll see it will just come out to 900 over x. Now, that's great. We've now got an expression for surface area just in terms of x. So this is something you're always going to have to do at GCSE level. You're going to have to get it in terms of one variable before we're going to be able to differentiate. And now we can go ahead and differentiate this. So, I'm doing d dx, where that basically means to differentiate this little expression that we've got, which we know is surface, an expression for the surface area. You see the 900 over x, I have rewritten to be 900 times x to the minus 1, using, indices laws. And remember, that's what we need to do here because it allows us to then use our power rule of differentiation. So you see 4x squared would become 8x because you do 4 times the 2 and then knock 1 off the power. The 900 x to the minus 1. So you're doing 900 times the minus 1. So it becomes minus 900. And then you knock 1 off the power. So minus 1 becomes minus 2. So we can differentiate both of them in the same way. So we've got the derivative. This is kind of like telling us how does the surface area of this shape change as we change the value of x. And what we want to do, we want to find out when is the minimum point. Basically, when is this rate of change 0? We know when a graph curves temporarily at that minimum point, the gradient's 0, isn't it? We saw that in a previous lesson. So that's the point we're trying to find. So that's why we set it equal to 0 there. And then it's just a matter of solving this equation, which might look a bit tricky, but all we really need to do here is multiply through by x squared to get rid of that dividing, like x to the minus 2 is basically dividing by x squared, isn't it? So if we times by x squared, we'll get rid of that. And you see we get this little cubic equation, which we can solve quite easily by moving the 900 to the other side, divide by 8, and then take the cube root. And if you do that, what you'll find is you get the answer of 4.8 for x. And, well, we could take that 4.8, we could put it back into our little expression for h there. So h equals 300 over 2 times 4.8 squared. That will give us the height as well. So great. We now have all the dimensions of this carton. We now have the optimal shape of this carton that will minimize the surface area but still have 300 centimeters cubed of volume. So so there's an example of a practical real life problem that's using all this math you've already learned but using it in this really useful way. And this is something that really like is done in the real world all the time, because companies, when they're manufacturing something, you always want to do it in the most efficient way. You don't want to waste material, you don't want to waste money, so you want to find the cheapest way of doing it. Well, this is the kind of math that's being done. Right, so let's leave it there. So I'll give you a similar kind of problem, but I've made it a little bit trickier to make it our challenge problem for the week. And a what we have here, right? So we've got a cylindrical rod that has a fixed volume of 10,000 centimeters cubed. So what we do, we have something like this, and the length of that rod is labeled L. The radius of that little circular bit on the end is R, so it's quite small. And it's a little bit different, this one. You see the curved area, so that area going around the cylinder, it costs us 3p per centimeter squared, whereas the circular ends on each end of the cylinder costs us 6p per centimeter squared. So if we're going to make this rod out of whatever material it's made out of, we want to find the radius and the length that minimizes the cost of this rod. So it's very, kind of similar to last time, but there's just a couple little extra considerations you need to make. I hope by looking at that example that we just did, most of you should be able to have a good stab at this one. So if you need some pointers, here's kind of the steps that we need to do here. Like, we need to use our formulae that we know regarding surface area and volume of a cylinder this time. And we want to try and express, say, the surface area in terms of a single variable that we can then, in the second step, we can differentiate that. And we can differentiate it. We can find out when is the minimum point using that derivative. And that minimum point will tell us where, our dimensions essentially for either R or L, and then we can find the other one. It'll basically give us that optimal solution where this rod will be the cheapest to create. Right. Okay, so that's that. So we're done with calculus now. Next time we'll be moving on to matrices, which is almost certainly a completely new topic for most of you guys. So yeah, we'll be looking into that. It's kind of related to vectors, or well, not quite, but they're used in conjunction with vectors a lot, and it allows us to solve more complex problems. So yeah, tune in for those. You'll see how that works. Right, so I will see you next time.